Hello and welcome to CAD Dimensions Lunch and Learn Simulation Suite Overview. My name is Franco Rotoli. I'm an applications engineer here at CAD Dimensions, and today we're going to be talking about the different products that simulation offers and the different levels of SOLIDWORKS, ranging from SOLIDWORKS Premium all the way up until Simulation Premium. If we take a look at what SOLIDWORKS Premium holds, basically it has the whole SOLIDWORKS lineup, including SOLIDWORKS Professional, which includes Toolbox and PDMWorks, and all the other SOLIDWORKS add-ins. But SOLIDWORKS Premium has something special. It has static analysis and SOLIDWORKS Motion, so two simulation packages. When we move up a level, we get into Simulation Professional, and Simulation Professional offers a much wider variety of analyses that you can do. Everything from frequency, optimization, drop test, fatigue, and thermal and pressure vessel studies. So we'll get into some of those demos in a minute. The highest level of simulation that we offer is Simulation Premium. That includes everything in SOLIDWORKS Premium, static analysis, etc., everything in Professional, as well as nonlinear studies, composites, and advanced dynamics. Today, because we are on a time schedule, we're only going to be covering these topics. So we'll do a static analysis, frequency, fatigue, thermal, drop test, and a quick nonlinear study. So let's get started with the demonstration. I'm going to hop over to SOLIDWORKS here, and we have a suspension assembly for a rally car here. And what we're going to focus on is going to be this bracket right here, this steering bracket. We want this to sustain. Actually, let me hop back over to the PowerPoint and talk about our goals for this study. So we're going to do a design validation for this bracket. We want to make sure we keep the stress below 150 megapascals. We're going to design it. We're going to do a fatigue study on it, so we want to make sure that it lasts an entire season of about 10 to 20 rallies. We're going to load it and unload it 1 million times using a fatigue study again. And we're also going to do a frequency study because we want to avoid frequencies in the range of 1 to 30 hertz, because typically the wheel motion generates about 27 or 30 hertz. So we want to make sure we stay out of that frequency range so that we don't hit any resonance. Okay, so we'll jump back into SOLIDWORKS, and using configurations here, I basically just turned off all the rest of the components so we can focus just on this component. So let's go ahead and start a new study. And if you have Simulation Professional, you will see all these study types. Depending on what package of simulation you have, it's going to give you a different amount of icons here. Okay, if you have only SOLIDWORKS Premium, you will only see static here. To turn on simulation, before I get ahead of myself, to turn on simulation, you just go to Tools, Add-ins, and make sure that SOLIDWORKS Simulation is turned on. Okay, SOLIDWORKS Motion is a separate add-in, and that is included with SOLIDWORKS Premium, remember. Alright, so let's go ahead and start a new study, and we're going to create a static study and say OK. For those of you unfamiliar with how to set up simulation analyses, we do have other webinars on our website, as well as the tutorials in SOLIDWORKS to go through and teach you how to set up analyses. So really quick here, I'm just going to add a material to this bracket, and it's going to end up being a custom aluminum material. Remember, the SOLIDWORKS and simulation databases, material databases, are fully customizable, so you can go in there and create your own materials. For fixtures, we're going to go ahead and do a roller slider on this back face. So basically what it allows this back face to do is move normal to this face, because in reality it's not welded to the plate that it's on. It just slides there. It's only connected to the bolt with the bolts. My next fixture that I'm going to do is called a fixed hinge, which basically simulates the bolts in these three holes. Okay, that's it for fixtures that I'm going to do. The next thing that I'm going to do is I'm going to add a load, a force load, onto this face. I don't want it to be normal, so I'm going to click selected direction, and I'm actually going to pick this face for my direction, and I'm going to add 6,000 newtons in this direction. And that's pretty much it for the setup. We can go ahead and run this static analysis, and again, so the static analysis is included in SOLIDWORKS Premium, and we can see here the reaction of our bracket with that force. I'm just going to hide this force so it stays out of our way, and I can animate any plot that I have very easily, so I can see what it's doing, and it is behaving as expected, right? I can see here that my max stress is in these areas, which is to be expected, and we're at 17,000 psi. Now again, just like with SOLIDWORKS, it's very easy to change all my units in simulation. I can just right-click, edit definition on the plot, and change it to megapascals. Remember, if I go back to my PowerPoint, we're looking for a max of under 150. And we can see here that we're actually at 122, so we're good for our static study. If I want to take a look at any displacements, I can certainly do that. So we can see here that the max displacement at this ball is about 0.1 millimeters, which is acceptable for our needs. You can also look at factor of safety. You can see that our minimum factor of safety is in this area again, and it is 2.25. I'm just going to go ahead and adjust the scale here because our maximum factor of safety is almost 3,000. If I adjust from 2 to 100, we can see a better color distribution in here. Okay. Okay, so that's our static study, and again, that is what is included in SOLIDWORKS Premium. We can do static studies just like that. We can add forces, pressures, you can even add thermal loads, which I'll show you later on. But typically that's what you would do in a static study. Let's move on to the next study that we're going to do. Is we're going to do a study for our fatigue analysis. So we'll jump back into SOLIDWORKS, and using this study, we're actually going to say, okay, now load and unload this 1,000,000 times. So I'm going to click on New Study and go down to Fatigue. Now this is included in Simulation Professional. And to set up a fatigue study, what you can do is you just right-click the loading, add event, and you attach it to any other studies that you have. So I have study 1 was the one that I just created, and we're going to go to 1,000,000 cycles. Fully reversed means that it's going to load it and then load it in the other direction, which is what's actually happening in this particular assembly, right? As it's hitting bumps and as it's turning, as you're turning the steering wheel, it's going back and forth, so it's loading and unloading. All right, if we go into our result options, we want to make sure that we look at the whole model, and finally we want to make sure that all of our materials get added. A beauty of SOLIDWORKS simulation is you can actually copy and paste your materials from one component to another. So if I go ahead and copy, I can paste that material to all my components. So let's go ahead, and now that I have green check marks on everything, I can go ahead and run this. It runs very quickly, and I have my results. I have two plots for my fatigue study. One is a damage and one is a life. If I double click the life plot, we can see that this is where we expect it to fail first, right? Because that's where the most stress was. And we can see here that our minimum life is about 2 million, which basically means that this would fail at about 2 million cycles, where we're at 1 million cycles now. And in here we're at 1e to the 8, that's our minimum. We're okay here. If I go to damage, here we can see that the damage is about, and it's in a percentage, so it's at about 37%. So we're at about 37% of the wear and tear that this joint is going to take at this location. Okay, so we're nowhere near 100% damage, and we're nowhere near using up all quote unquote using up all the life of this component. So we now meet our second requirement. Let's jump into the third requirement, which is the frequency check. We want to check the natural frequencies of this component. So let's go ahead and create another new study. And we're going to create a frequency study where, again, I can copy and paste or even drag and drop the materials from there to there. So from study 1, I can drag and drop the materials. I can drag and drop the fixtures as well, because obviously that is going to change our natural frequencies. I'm not going to add any external loads because I don't want to add any loads to study the frequency of this. I certainly could, but I'm not going to. You can even, if the geometry doesn't change, you can even drag and drop the mesh, which is the mathematical model that simulation creates, which again is going to save time in our study. So I'm going to go ahead and run this. Again, this runs very quickly. And we can see our first 5 modal shapes. If I just double click on these, you can see that. Looks like this one is the first twisting mode. I can right click and animate here so you can see what it's actually doing with this modal shape. You can see that's at roughly 7,000 hertz. If I want to see all the mode shapes that I solved for, I can just right click the results folder and say list resonant frequencies. So it's solved for 5 modes, and you can see here we're nowhere near our 30 hertz. So we're good to go for this. Okay, so that's a quick overview of these 3 analyses. We did the static, right, where we just loaded it. We did a frequency just now, and we also did a fatigue where we loaded and then unloaded using the static study. So we already jumped into Simulation Professional with these 2 studies. The next thing we're going to do is we're going to do a thermal study on a spark plug. Okay, so spark plugs, our goal for this study is to determine the stress distribution caused by the actual spark. Okay, rather than generating a spark in simulation, we're just going to heat this area up to 1,000 degrees and see what happens. So let me open up this component, or this assembly I should say, and let's take a look at how to set up a thermal study. Again, we just go to New Study and we pick Thermal from the list. I already have a thermal study set up. I'll just walk you through how to do it. It works exactly the same way as all of our other studies. So we define materials. So I have plain carbon steel down here, silver at the node up here, plain carbon steel, and ceramic for the bottom. Okay, so obviously each one of these has different thermal properties. I added a temperature load, so rather than force loads, we have thermal loads. So you right click, I can add temperature, convection, heat power, heat flux, and radiation. I added a temperature load to these internal faces of 1,000 degrees Fahrenheit. I also added convection coefficients because these are going to be convecting or conducting to, in this case, the engine block. So this is going to be a convection coefficient of 0.0008 with an ambient temperature of the engine block being 300 degrees Fahrenheit. I also added a convection coefficient here, which is a little bit higher, 0.001, with an ambient temperature of 200 degrees Fahrenheit to the open air next to the engine block. We mesh it the same way, we run it the same way, and let's take a look at our results. So we have a temperature gradient plot where we can see here, obviously where I added the temperature, it's at 1,000 degrees Fahrenheit, and out here in space, in the open air, it's about 200 degrees, which is what we set the ambient temperature at. I can right click this and I can do some section clipping, which basically I can cut this in half so I can see the temperature gradient through my component. Just like every other simulation, I can right click and probe, so I can actually take points and I can see the temperature distribution through this component in this case, and I can also plot it on a graph. Okay, so I can see the temperature distribution through the thickness of my component here. You can also save that out to a comma separated file, so a CSV file that you can import into Excel. The next thing we're going to do is we're going to take this thermal study, because all this does is plot temperature gradients, and we can import this into a static analysis, a stress analysis, so we can see what stresses are induced by our thermal loads. To do that, again, we go to New Study, and we're going to do a static study. And this time, for our external loads, I can right-click and go to Thermal Effects, which brings me to this screen, and I can import temperatures from a thermal study. All right, I only have one thermal study in this case, which we were just looking at, but if I had multiple thermal studies, I could pick which one I import. And what that's going to do is it's going to add an external load that links it to this thermal study down here. Same idea, we can drag and drop materials, we can add any fixtures. In this case, what we're going to do is, because this is screwed into the engine block and there's a collar that goes around here, we are going to add an on-cylindrical face restraint on this face so that it cannot move axially or radially, or it cannot rotate either because it's screwed into the engine block. Again, that takes a second to run, so I already have one created. And let's take a look at the stresses. All right, so we can see here that the max stress is about 2.5 million newtons per meter squared. We can also take a look at our displacements if we need to. So our expansion, we're looking at about 0.1 millimeters at this point, which is more than acceptable. We can also look at factors of safety, and it looks like our factor of safety, our minimum factor of safety is 0.1. We may actually be breaking this geometry, so I'd want to make sure that that 1,000 degrees was accurate and that this entire thing was actually 1,000 degrees. So you're just, again, going to want to be careful. This is going to give us some good insight into what's going to happen with our components. Okay, moving on to our next study is going to be our next generation cell phone drop test. We can see we have a very advanced cellular phone here. So we're going to drop this phone from 6 feet onto this corner down here, and we're going to see what happens. We also want to determine if the screen will break due to the deflection. So the LCD screen that's in here, we're going to watch one of these corners and see what kind of deflections we get to see if our screen can withstand that. let's go back in here to SolidWorks and open up this phone assembly. All right, what I did was I added a sensor. For those of you who don't know, you can add sensors in SolidWorks to monitor pretty much anything. You can monitor dimensions, mass. You can also monitor simulation results. So you right-click the sensors folder and click Add Sensors. So mass properties, dimensions, interference detection, etc. We're going to do simulation data and workflow sensitive, which monitors all simulation data. And basically what my sensor was is monitoring this corner. So let's go ahead and set up the drop test. So we click New Study and Drop Test. And setup for a drop test is very, very easy. All you do is you apply the materials, obviously. I'm just going to apply a material to all of these, and we'll just make this out of medium high impact acrylic. And we right click the setup where we define either the drop height or the velocity at impact, so I can fire this at the floor if I want to, or I can drop it from, in my case, from the lowest point. I want it to be 6 feet off the ground. I give it a direction for gravity. In this case I have a plane that's askew a little bit, so that way it's going to hit on this corner. All right. If I wanted to change the target orientation, so if I wanted it to move, accelerate in this direction, but I wanted it to hit in a different direction, I could choose a different plane here. But in this case, we're just going to pick normal to gravity. I could also supply a friction coefficient to the target, or the ground in this case, and I can specify whether it's a rigid or flexible target. We want worst case scenario, so I'm going to keep this on rigid. I can also apply a critical damping ratio, so it'll actually dampen as it hits, or as the stress propagates through. We're going to leave that at 0 for right now. And we right-click Result Options, go to Define Edit, and what we're going to do is we monitor how long after impact. In this case, I'm going to do 200 microseconds after impact, and we want to save results starting from 0, number of plots 25. And this is where we monitor our sensor. Okay. We run this. Now this does take quite a long time to run because again it's doing it in it's taking loops, and it's doing loops. So what I do is I already have this drop test run, and in the results we get the same results. So we see our stress distribution. And here we can see I created a very coarse mesh just for speed's sake. Our displacements, strains, and our response graph. This response graph is monitoring that vertex that we specified in here. So it's showing the displacement of this point over time. So we can see here we actually probably didn't monitor long enough because it didn't settle out. But we're already at 1.4 millimeters roughly, or 1.35 millimeters. So in likelihood, the screen is going to crack because of the deflection at this point, depending on what the other corners do, obviously. And now for the fun stuff. This is what everyone wants to see, right? We want to see this thing actually dropping. So I go to my stress plot, I can right-click Animate that, and we can see it dropping, and we can see the stress propagating through. I'm going to change my resolution here real quick just so it slows down a little bit more. Okay, so you can actually see the stresses propagating through the component. And this is up to 500 microseconds after impact. Again, I would probably want to do at least double this just to see exactly what's going to happen. Okay, we can see here that if I look to the right on my stress plot, we are past yield at some points, and we can see that the red is down here. So, and we can actually follow the max stress. It's always down here. So this is actually breaking. The acrylic is actually breaking. So from 6 feet, this thing does in fact break. Okay, so back to the PowerPoint. So we see the stress is when dropped from 6 feet, and we determine that the screen will break due to deflection in this area. It is very likely that the screen does crack. The last study we're going to do is our nonlinear study, and again, this is in SOLIDWORKS Premium, or SOLIDWORKS Simulation Premium, excuse me. And what we're going to do is we're going to simulate this rubber gasket that goes onto a door. You can see from the picture here that the gasket is long. We're going to take just a slice of it, again, just to speed up time. It is symmetric about, it is half symmetric going through this way. The profile is just an extruded profile. And this could be as long as you want. We're going to take advantage of symmetry to show what's actually going on in the gasket here. And we're also going to load it and unload it. That is an advantage of having the simulation premium, is that you get to control how your loads work over time as well. Not only do you get your nonlinear materials like rubber, you get a bunch of different nonlinear material models. We'll jump into that in a second. But you can control how your loads and restraints work over time. You can see from this graph, and I'll show you when we get into it, that we're going from time 0 to time roughly 0.5 seconds. We're loading it, and then we're going to unload it at 1 second. We're going to unload it and make the force 0. All right. Okay, so you saw from that picture that the gasket was rather long. Again, we're just taking a slice of it, and we're going to use a symmetry restraint to just take a look. And again, just for speed's sake. How we're going to do this is we're going to fix these edges in here, or these faces in here, as if it were in a door. And we're going to move this block as if it were the frame of the door 7 millimeters up, or I believe 7.5 millimeters up. To do that, again, we have materials. Again, we follow the same process over and over again. The material, let's take a look at that real quick. It's a rubber material. In our nonlinear analyses, or in our nonlinear package, we have our linear elastic isotropic material, which is the default, but we also have nonlinear elastic, some plasticity models, 3 in fact, the von Mises, Tresca, and Drucker-Prager. We also have hyperelastic material models, viscoelastic, and Nitinol models. For more information on that, give us a call, and I'll be more than happy to discuss those a little bit further. But in the interest of time, we're just going to keep this as a Mooney-Rivlin material model. The door frame is going to be carbon steel. It doesn't matter what it is. It's significantly harder than the rubber. That's all we need to know. For contact sets, we're going to apply what's called a no penetration, which means that at these two locations right here, this material can actually slide along this rubber, or the steel can slide along the rubber. As I mentioned, we fixed these edges in here as if it were bonded or glued to the door frame. Okay, so we're going to move this geometry up 7.5 millimeters. But as indicated by our slide, I want to move it up 7.5 millimeters in half a second and then move it back down. So in a nonlinear study, you have this box, variation with time. I can click on curve and edit the curve. And this is basically a little spreadsheet. So at 0.5 seconds, I want it to go the full 7.5 millimeters. I'm going to add a row, and at 1 second, I want it to go back down to 0. So our time curve looks like this, or our loading curve looks like this. We say OK, and run the analysis. So we can see the results in here. If I edit the stress plot, we can change which plot we're looking at. This is at 1 second. You can see it moved back down to here. I can also animate this so it cycles through the motion. Change this down to a higher resolution so it goes a little bit slower, and we can see exactly what it's doing. We can also plot the deflection just as we did before. We can probe the displacement, for example. We can show the displacement. We can probe this point and actually watch it over time, which it acts as we expect. Okay, in conclusion, these are the packages that simulation includes, so everything from SOLIDWORKS Premium all the way to Simulation Premium. If you have any questions, please feel free to use the chat dialogue, and I'll be here to answer some questions. I'll stay on the line for a few more minutes, and we can answer your questions. Thank you very much for your time today, and again, check out our website, www.caddimensions.com, for all of our webinars that we've had, as well as other tips and tricks and other great information. Thank you again. My name is Franco Rotoli, and I'll field your questions now.